So I will start with a little bit introductory part about divergence. And I tried to make my talk accessible to graduate students, which I don't see many in the audience, so I apologize if it's too easy for you. But let's talk about divergence. It's a large-scale invariant of metric spaces. So we start with a geodesic metric space and look at sphere with a base point. We look at sphere of radius r around base point. And then I'll draw a sphere here. Look at points on a sphere. And look at the so-called r-avoidant paths from one point to another. What does r-avoidant means? That they lie outside of the sphere. So, and among all arc-avoidant paths, we take the one which is the shortest. So here, for example, we'll go along the sphere itself. So that's what stands in this parenthesis, lengths of r-avoidant path from x to y, and we take infimum, which I denoted by red. And then we take a supremum for all points on the sphere. And here, for example, such point will be here. The antipode. It is supposed to be antipode. Divergence is a function of radius, and it gives us the length of maximal length of r-avoidant paths. In a way, you can, I have a funny analogy, it's a worst student in honors calculus class. Like, this is your students in paths which lie on the sphere. They are in honors class, and the worst is the farthest down. So that's the well-defined invariant of metric spaces, of geodesic metric spaces. And considering examples reveal some interesting phenomena. If we look at, let's say, Euclidean space, then the length between antipodal points on the sphere is approximately, well, it's linear in radius. So we say that divergence is linear here. However, if we look at, let's say, hyperbolic space, we also can talk about spheres there or circles, but the well-known formula for the length of circumference involves hyperbolic sine. So divergence is pi times sinh pi, which is exponential in R asymptotic. So that is a simplest example of dichotomy, that in Euclidean space we have linear divergence, in hyperbolic exponential.
That's a good question.
Yes, please.
Is it always, are you always sort of measuring the distance along all in whatever metric space that you're in, or is it possible that the shortest path length?
Yes, it is possible that the shortest path can be weird. All we care about that it avoids the open ball of radius r. There are, in some spaces, are dead ends where you cannot even extend some geodesic. So interesting things happen. Yeah.
So is this kind of analogous to this growth of groups between linear and exponential?
Growth.
Growth of groups, right?
Growth.
Yeah.
That's an interesting analogy. And I know that both growth and divergence are quasi-isometry invariants of groups. But I think this is maybe different.
But then you have this kind of sub-exponential growth, right? Like these examples of growth.
Yes, there is sub-exponential growth. And the point of my talk that there are polynomial divergence and I don't know yet examples which are bigger than polynomial and less than exponential. That's an interesting question.
Because those that happen for growth of groups, right? That was
Yes, yes, that's famous example. Yeah. However, a different property of divergence is that if X is a product, then divergence is always linear. And that's a remarkable divergence. X is linear. And it's very easy to show, actually. Let's say this is my space A, this is my space B. I have some sphere, and I want to estimate what would be, let's say, length of path between two points of the sphere. Well, we can extend in each direction, and our path may look like that. We go until we reach length r in one component, then q the other component, then extend it back to r, and do the same from other point. And they meet here. That would be maybe not here. Yes, so we see what happens. This way. And that is our avoided path, which consists of 1, 2, 3, 4, 5, 6, at most 6 segments of length r. So we see that the avoided distance between x and y is less than 6r. And that's very easy. Talk shows that as soon as we have product of spaces, the divergence will be linear. And growth can be hidden here or here in a non-trivial way. So it's slightly different from growth, but also quasi-isometry. So Gromov, in his seminal article on the early 90s, suggested I avoid using the word conjecture because he was vague or maybe writing not in a very formal language there, that this dichotomy holds for Cat0 spaces as well. which dichotomy? Which I mentioned there. So this thing generalizes to symmetric spaces of non-compact type. So for Euclidean ones, divergence is linear. For non-positively curved ones, divergence is exponential. So that led Gromov to suggest that maybe for cut-zero spaces, the same would happen. And what are cut-zero spaces? Cut-zero spaces generalize both Euclidean and hyperbolic in the sense of H. And they are defined in the language of model triangles. So we have a triangle of geodesics in our space X and corresponding triangle in R2. So that's length ABC, this length is ABC. They always exist by triangle equality. So the defining condition, if we go length P here, length U here, and consider corresponding points P bar, U bar here, then one distance will be less than or equal than the other. Distance between P and Q in our space X will be less than or equal than distance in R2. If that happens, we call that a cut-zero space. So that was Gromov's suggestion, and for quite a while, people believed that it may be true. However, geometric group theorists have produced counterexamples to that. So Gersten, so Gersten in 1994 came up with a group with divergence R squared. So these are all cut-zero examples.
So here the metric space is the Cayley graph?
Yes, we can say so. Or we may say that it acts properly compatible by isometries on some space, quasi-isometric to Cayley graph. Where Cayley graph can be one skeleton of this space. Yes. So that space would be cut-zero because Cayley graph is one-dimensional. But if group acts geometrically, as they say, it's properly discontinuously by isometries to compactly on some space, then I think I should have some word spaceful. Then Cayley graph is embedded there by isometric. There are more than one dimension of spaces. So that was example of Gersten. Then Natasha Matsura in 2013 came with examples of any polynomial R of G. And when I say polynomial, they are all considered up to equivalence relation, which makes irrelevant the constant. So all we care is the power. The constant is hidden in this equivalence relation. And very recently, Brady, which was mentioned in previous talk, author of McKeown, but now he authored with.
Wait a second. There are two Brady's. So
Yes, they are brothers anyway.
I know. One is Dr. Hall, one is Ignat.
Noel Brady. From the University of Oklahoma, who happened to be my advisor, and Hong Tran, who's also a postdoc in Oklahoma. They came up with examples of remarkable R to the alpha with alpha dense in 2 infinity and R to the n log R, where n is positive numbers. So these are all K0 examples. So we see that divergence in class of even K0 groups delivers very interesting examples, and groups are rich and have non-trivial properties. That's what I wanted to tell you about divergence. And now, natural question would be, given your favorite class of groups, what kind of divergence they exhibit? Okay. Natural question. Given your favorite class of groups, what divergence functions are possible? And the point of interest of my co-authors and hence of me when I was introduced to this project was Coxeter groups, which are intimately related to the Artin groups and which are in some generalizations of braid groups, and hence the topic of this conference. I was hoping that I was afraid that speaking of Coxeter groups is too far away, but seeing previous speakers using Coxeter groups, I was really okay. We speak about Coxeter groups, people know them, people like them. So I prepared a little bit of definition, but I don't know, should I go with that or we can skip it? So it's defined that the Coxeter group is given by the following data. A finite set of generators S and matrix of symmetric matrix of MST, which consists of integers, positive integers, or simple infinity with the property. On diagonal, we have ones, and all others are from 2, 3, 4, etc. union infinity. And a group W is given by presentation S, ST, and ST equal 1 or all ST. What does it mean? So MST equal to means that we have ST equals ST equals 1. So MSS equals 1 means S squared. So in a way, no, in an exact sense, Coxeter groups are quotient groups of Artin groups by this relation. So it is encoded by the so-called Coxeter graphs. Sometimes they are called linking diagrams with very little difference. They are almost the same. So the two vertices are disconnected, S and T. If MST equals, they are connected with one edge. If MST equals 3, they are connected with two edges. If MST equals 4. Other than that, we just write what is there. And separate notice, if we have MST equal infinity, that means no relation involved. Now, there are famous classes of Coxeter groups. So, notable classes. First are spherical. The same as to say finite. And they were irreducible, are given by the following list, classified by Coxeter himself. And we see that this list corresponds to not corresponds, but resembles the famous list of classification of simple algebras, with the exception that there are some weird groups like H4, H3, I2, which can be not just 2, 3, 6, but any number. So that's the so-called non-crystallographic groups. They don't correspond to Lie algebras. It's simple Lie algebras. Then there is a finite groups, which are given in terms of extended linking diagrams if we add maximal root, then what would be? I listed special cases of this independence on the right because sometimes it's hard to figure out how they move. And also a notable case is the so-called linear hyperbolic ones. So these are exactly the reflection groups in spaces of a simplex in either sphere and dimensional or Euclidean space or hyperbolic space. So you take a simplex in each of these spaces, if it and reflection group in this the complex simplex. In these spaces correspond to spherical, affine, and hyperbolic groups defined by Gromov. For example, described by line. The triangle groups is something that previous speaker talked at the end. And interesting property that these two classes form minimal non-spherical Coxeter groups. So now I'd like to talk about our results that we obtained about divergence of these Coxeter groups. So let W be a one-ended Coxeter system. If it's irreducible and non-affine, then divergence of it is at least quadratic. I probably should have mentioned that divergence is defined for spaces which are, sorry, click automatically. Which are one-ended. One-ended spaces is such that after we delete any compact set, the rest is connected. So we can reach any points outside
On any compact, I mean,
sufficiently large, but arbitrarily large compact set. We get the difference is connected. Otherwise, we cannot imagine that we have something like that, and we erase the black part. There is no way we can get from here to here outside the set. So divergence will not be defined. It will be defined as infinity, but not a useful notion. So we need to restrict ourselves to spaces which are one-ended. For example, R is two-ended. Once we delete any compact set, we have two ends, three ends. So there is a easy criterion to tell when a Coxeter system is one-ended. One has to look at the number of spherical subsystems stated in various books. So our first theorem tells that if W is irreducible and non-applied, then divergence is at least quadratic. And then we get a complete characterization of linear divergence.
So what is the one that is space that analyze here? Again,
Yes, that's a good question. Thank you. So each Coxeter group acts on cat0 space, which is called the Davis complex. Essentially, it is glued from the spherical cells following pattern of reflection. So they develop and Davis complex. It's has nice properties. It is cat0. And Cayley is one scale. Quasi-isometry. Yes, so one-ended in the sense of Davis complex. I should have said that. Yes. So these are the following cases when we have linear divergence. If and only if we have direct product that corresponds to the picture which I talked before, direct product of infinite spaces have linear divergence, or one can be finite and other irreducible phi of rank bigger than 3. Why it is so? Because the phi subsystems, they affine Coxeter groups, they have Zn of finite index. They are the so-called hypergraph groups. So they act geometrically on Zn. So they have this product of finite index already there. And next corollary is if a one-ended Coxeter group has a superlinear divergence, then the divergence is at least quadratic. That means there is a gap between R and R squared. In class of Coxeter groups, there is no intermediate divergence between R and R squared. So it is a similar situation with gain functions. If you are familiar with them, there is also a gap between linear and quadratic. By the way, divergence can be sort of a filling function to fill zero spheres at infinity. So pair of points is a zero sphere outside of radius of R2 of R points in the neighborhood of infinity. And we are looking at the shortest path outside of this radius. So we are filling a zero sphere with one chain, so to say, of minimum volume, minimum mass. That's how it fits in the general Riemannian geometry where we fill cycles with surfaces, linear surfaces, etc. So next results, we define a hypergraph index, which is an integer or symbol infinity computable directly from Coxeter graph. And it shows us when, if h is 0, group has linear divergence. If h is 1, group has quadratic divergence. This is if and only if. This is just one direction. We're able to show it only in one direction. So if h is finite, the divergence is bounded above by a polynomial of degree h plus 1. And if h is infinity, that's if and only if the divergence is exponential. We conjecture that we can reverse these two arrows. So And this hypergraph index captures the order of divergence Z. However, we haven't proven it yet. That's our working project in progress. Another pieces of our results relate hypergraph index with Betty number. So we look at the graph, the Coxeter graph, and Betty number is number of edges minus vertices plus number of components, or rank of first homology. And the statement is, if H is finite, then it's bounded by its number plus 1. And in particular, if Coxeter graph is a tree, then divergence is either linear, quadratic, or exponential, and nothing else is possible. And all these possibilities are realized. Now, the definition of hypergraph index is a little bit technical. I will try to give you a general idea in the minutes that I have left. So there is class of idea. There is class of Gromov hyperbolic groups. They have divergence is exponential, and they cannot have Z plus Z subgroups. Then there is a class of relatively divergence is also exponential for them, but they can have Z plus Z subgroups. But only inside the peripheral subgroups. These are part of this notion. Relatively hyperbolic groups are hyperbolic relative to a family of peripheral subgroups. So this Z plus Z subgroup should be hidden there. So
it's like a fundamental rule for hyperbolically complement.
No. Gromov hyperbolic groups are defined in terms of thin triangles. So if you take Cayley graph or
yeah, but the fundamental rule for hyperbolic manifold is Gromov hyperbolic.
not necessarily. For example, complement of figure 8 node.
Yeah, that's what
They have Z plus Z, like
they're relatively hyperbolic.
relative.
Yeah, that's what I was
Yes, they are here. You were talking about relative.
yeah, of
Yes.
course. Right. So that's the torus on the boundary of the leaf, right?
Say it again?
The torus, right? It has a meridian and longitude.
Yes,
That's
yes.
the Z plus Z.
Z plus Z subgroup, yes. So if we consider them a peripheral subgroup, then they exhibit hyperbolic behavior. Yeah. So the idea is to so Capras proved that Coxeter group, if it is relatively hyperbolic, the peripheral subgroups are special or parabolic, that is given by a subset of generators. That's what it means, special parabolic. We fix a subset of generators, and peripheral subgroups can be found in this subset.
Finite subset.
Fine. So to build such relative, so to tell if a Coxeter group is relatively hyperbolic, and hence the divergence will be exponential, we try to start with all subgroups of type Z plus Z and try to organize peripheral subgroups which have which contain them. We start with Z plus Z subgroups and classify them in special subgroups. Subject to some conditions, some rules. The best is to look at certain Coxeter group. So double edge means label 4. One edge means label 3. No edge means label 2. That's common. Rule for Coxeter graphs. So if we look at what we have here, and what we have here, there are two subgroups. One of this type and one of this type. They are both non-spherical. So their product contains Z plus Z. Similarly, this one is the same. So same here. Of this or of this. So we need to take union of this spherical subset. Sorry, of this special subset. And this union turns out to be exactly the whole S. So T1 and T2 are without this red lines, so T1 union T2 holds S. And this tells us that hypergraph index is 1 because this process stopped just after one step. I understand that I'm saying something not very coherent, but let me give you just a picture of few examples. So that has hypergraph index 0 because it's affine. So affine has Z8 actually. This has hypergraph index 1, and I tried to explain why. If we follow this logic, this one has hypergraph index 2, and this hypergraph index infinity. So this divergence of this is exponential, divergence of this is quadratic, divergence of this is linear, and divergence of this is bounded by cubical polynomial. So I probably stop here, and if you are more interested, I can tell you about this in person.
Just, can you go to corollary 3? Where there was no, nothing between
Yes.
r and r squared. For things that are not, I don't know, for different things, is this gap, like, is that common to have the gap? Is it not common to have the gap? Do you know? Do you know?
I don't know examples where there is something in between. Maybe this Brady and Trent example, they have n times look, but I forgot. Does their power start from 1 or from? I need to double check. So if it starts from 1, then they have not from 2. But this behavior gap between r and r2 is a famous thing for Dane functions.
Oh,
Yes. The functions when we fill one circuit in Cayley graph with disks in Cayley graph. So we measure how many times we need as a function of length of the circuit. So in that sense, there is also a famous theorem of radial price. Yes, please.
So this is for one-ended, right? But you said
Yes.
something that if it's not one-ended, that the divergence infinite can be met. So for a group, you can have either 0, 1, 2, or you can do it.
Yes.
Right?
Yes.
Just ignore almost 100 years. So, but generally the groups have been for one end. So what happens if you don't have one end? If you have, let's see, looks more like a free.
I know that in article of Drutz's Sapir and the Soroko author, they have some generalization of notion of divergence for many ends, but it's not as natural in my opinion.
But in your definition,
I need one end,
groups with infinite ends will have what kind of divergence then?
just constant infinity, constant function equal infinity.
And if they have two ends, same thing.
Yeah.
But 0 ends, then it's just a polynomial.
0 ends, it's well, linear because of this equivalent explanation, everything is bumped up to so that it's quite also yes.
So 0, 1 end.
Yes, 0.